Alright, in this video we're going to use LTspice to simulate real transistors, or at least the transistors we're going to use in the lab. This is still a CMOS inverter. We're using an NMOS transistor to PMOS transistor, BS170 for the NMOS, which we've used before, and a BS250 or 250P, and that is a PMOS transistor, which we get to use on Thursday. So here we go. What we want to do really is not type in the models, but we want to find our own models. So we want a BS170 SPICE model. The ones we're using are from Fairchild. So we found Fairchild's information here. We go down and down and down. Notice that I'm signed in. If you want Fairchild's, you have to have an account with them. Free sign up. So models. Here's a link here. And we just wait a second. Here it is. Alright, so let's save this to a nice place. How about LTspice homework 20? So bs170.mod, it's clearly not a VLC file. We'll see that it's just a text file. Alright, so there's BS170. We want the BS250P SPICE model. Let's see if we can find it. Alright. What we want is the BS250P. Diodes Inc. is the manufacturer of this. We can look at the data sheet if we want. And that's what it looks like. You'll be familiar with that on Thursday. I'll leave the data sheet up here. And also the BS170 up. Where's the data sheet? There it is. Alright, but we want the SPICE model for the BS250P. So BS250P.text, that's fine. Alright, next is going over to look at these models. Really all we're going to do, we can use these separately. I'm just going to put them in a same text file. So we're going to edit both of these in Notepad++, make a new one. So first one, select all, Control-C, Control-V. What's up with this? I don't like these leading spaces. SPICE doesn't maybe not like leading spaces either. So I'm going to find and replace. I'm going to find the regular expression that, 4 spaces, replace it with nothing, find the next one, replace, it's going okay, replace all. Hey, all done. I don't like to use the keyboard if I don't have to. While we're at it, we're just going to save this. So we're going to call that FET models.txt. The extension doesn't matter. It's a text file. SPICE doesn't care about that. Go down here. I'm going to go like this. Drain, gate, and source. That is the order that they go in. That's what we want to do. We want to check. This is a subcircuit. Subcircuit BS250P. It's 3 terminals. The body connection is implicitly tied to the source for this. We have a single MOSFET transistor with a certain model. A gate resistance. You see the gate is terminal 3. And that's terminal 3. Or the terminal 4 is the gate. Well, terminal 4 doesn't go to the gate of the internal MOSFET. It goes to a resistor. 160 ohm resistor is in series with the gate. So that models those. The resistance of, say, the polysilicon. RL, source, to between 3 and 5. RL probably stands for R leak. It's a very large valued resistor between drain and source that represents leakage. A couple capacitors, and our diode from 3 to 5, and 3 to 5 is drain to source. That diode's there anyway, but they're going to model it separately here. So here's this. This is inherently a SPICE level 1 model. Uses the square law equations. And so on. So we have that, a threshold voltage of minus 3.2 volts or so. We'll come back to that for sure. Next, the BS170, Control A, Control C, Control V. This is humongous. So it's a subcircuit. It's called the BS/MMBF170. The MMBF170 is just the surface mount version. We see this one has 4 terminals. 1, 2, 3, 4. Hey, a little key down here. 20 is drain, gate, source, and then 50 is V temp. What this is we're using SPICE, and we're making a fake circuit inside here that also models the temperature. We can vary the temperature of this device separately than we can vary the temperature of the whole simulation, which makes sense, right? The transistor heats up and nothing else heats up if that's the case. However, we just want a 3-terminal model, and we don't have a circuit for this, and we can use it. So what we're going to do is take it off. So first order of the day, copy, paste, comment out the old one just so it's there. We're going to remove terminal 50, but we have to deal with where 50 is. So let's find 50. 50 is here. That's VTemp. That's not what we want. We want to find it in our subcircuit. So ED. This is it's a special SPICE voltage source, really. Output between here and 101 and 0. It's a control voltage source. It's a value. And this expression here, the brackets say make a calculation SPICE before you put in a number. The difference between node 50 and node 100. Node 50 is the temperature. I'm going to guess that this temperature is in Celsius, not Kelvin. We'll see that it's probably true here. So what's node 100? Highlight this. Thank you, Notepad++. Nope, node 100 and 0. It's a voltage source, VAMB, and it's set to 25 volts. How about an ambient temperature of 25 volts? Yeah, I think we found it. So node 50 doesn't show up anywhere else, and it's used to find a difference between the temperature that it was tested at, the model was created at, or assuming, and that. So we can do this, deal with temperature differently for this device that have chosen to do that. What we want is we want an ambient temperature. We're going to just set this. We're going to make a VTemp as in a temperature going from node 50 to 0, and we're going to set this to 27, because remember 27 is the default temperature that LTspice uses. We're going to do that. Put a note here. And the note is that because we're explicitly defining the temperature here, if we do that, we can get some weird situations. The temperature of the MOSFET here is some other temperature if we're varying temperature in the SPICE simulation, but the temperature compensation isn't going to track. We might have to do that as a note to self in here. So we're just going to put a note there for posterity. So we have a 3-terminal FET. We dealt with the V temperature, and the rest of this, we have several MOSFETs in here, several diodes, lots of diodes. This is possibly a more accurate model, but we shall see, won't we? Alright, so let's go back to our circuit. Here it is, LTspice. We're going to add our MOSFETs in here. This is really homework 19, copied and pasted, with some changes, and I'll tell you about the changes as we go along. First major change is instead of just a pulse waveform, the voltage source driving our gate, we're going to model the function generator. Function generator will model as this pulse voltage source, but it has an output resistance or an output impedance of 50 ohms. We need to include that in SPICE, otherwise our waveforms will absolutely not match. Let's add some MOSFETs. So these are 3-terminal MOSFETs. We want NMOS, not NMOS 4. So we'll do that. We'll add it here. Where should we put it? Looks good. We want a PMOS transistor. We want PMOS, not PMOS 4. And we want the source. I'm going to hit Control R, rotate, rotate. Control E mirrors so that the source is on the top. There it is, F3 to start wiring this up. It's easier to do it like this if we have a native 3-terminal model than it is to use the 4-terminal one. We would have to otherwise modify our subcircuit to use 4 terminals instead of 3. Alright, so the PMOS transistor is not a PMOS anymore. It is a BS250P. The NMOS is a BS/MMBF170. There we go. Our load capacitance we're going to set to 2 picofarads. That's about the capacitance in between the various strips on the breadboards. So we're going to model that as well. Here we go. Also, the pulse source, we set this to go from 0 to VDD. VDD, I made a parameter. It's in a brackets, so I can change VDD in one place on the schematic, and it changes the power supply in all the other places. It's like using a variable and parameters and functions and such. This is the SPICE version of doing that. So it's going to go from 0 to VDD. It's a logic level signal. No delay. The rise and the fall times are set to 15 nanoseconds. Why? Because that's about the rise time of our oscilloscope. This is the oscilloscope data sheet. Look in here, the waveform generator. It doesn't actually say 50 ohm output impedance on here. But if we go down, we say amplitude 5 volts peak to peak into high Z, so into an open circuit, or 2.5 volts peak to peak into a 50 ohm load. Well, if we take a Thevenin equivalent voltage source, that has a output impedance. If it drops by half into a 50 ohm load, that means it has a 50 ohm output impedance. So it's really not mysterious to us. It just wasn't explicitly named under a bullet point. Alright, so we're going to set this to a square wave pulse. We're going to do a megahertz or so. Rise and fall time of 18 nanoseconds. Back in lab 1, we measured everybody measured rise and fall times of less than 18 nanoseconds. 15 is a nice round number, and I think lots of people had rise and fall times at that. So we're going to simulate with that as well. We want to be as realistic as we can. Our high period of our waveform is going to be 100 nanoseconds and 200 nanoseconds, so we just get a nice square wave. There we go. Will this simulate? By the way, these measurements are almost copy-pasted from homework 20 or 19. This dot param, VDD equals 5. Remember, VDD was over here. We need a voltage here. We need to perform a calculation. VDD is here. We're doing this as a parametric. See, I don't want to change this in 2 places if I change the power supply voltage. I'm going to set it as a parameter or a variable in programming speak, and we also have to define it over here. Right now we're just setting it to 5 volts because that's what we will be testing at. I was playing around with the circuit and changing the power supply voltage. Let's run this. We'll do a transient simulation. So transient simulation, just over a period or so, 300 nanoseconds. Run. Oh my goodness, can't find definition of model. Said okay, we're just going to cancel. So view SPICE error log. Yeah, nothing out there because nothing happened. SPICE netlist, here's what's going on. V pulse, V supply, our capacitor, our resistor. We have 2 MOSFETs, M1 and M2. These are the names. Where's our model? Well, it says dot model. Yeah, ignore that. BS250. These are subcircuits. So these are not M. They have to start with an X, which is the SPICE prefix letter for a subcircuit. How do we do that? Well, first of all, we need to get these definitions in here. We need to include an include statement. Let's do that. .inc vet models.txt. So now we have them included in here. I like these all lined up, a little OCD about that. And then I don't lose things on the schematic. So save this. Can we run it again? Let's try it. Oh no, it's not going to work. What's going on is these are MOSFETs, not subcircuits. It's a symbol. If we want to change this, we could right click, try to do this pick new MOSFET thing. That doesn't work. Hold down Control and right click on here. So Control and right click. Instance name, value, these are all what we set. Remember last time we set this other line to visible to see the widths and the lengths. These are discrete transistors. We're not changing the widths and the lengths. We do want to change the prefix. We're going to change the prefix to X to make sure that SPICE, or the simulation engine part, picks it, assures that this is a subcircuit. So right click or hold down Control, right click on the other MOSFET, change that to an X. This is the key part right here. We need to change the prefix. Now we can run this, and it ran. Let's look at the netlist to see what happened. So here, X, M1. And now this is a subcircuit. It has 1, 2, 3 nodes and a name. That's how we do subcircuits. And down here we have include. Those models in that text file, which is right here, are subcircuits. And there's the name. There's the three nodes. That's how SPICE knows how many nodes we have of each type. So let's plot the input. Let's plot the output. Oh my goodness, this looks horrendous. No, it's actually about how it will look in the lab. So when the input goes up, this is V in. It's not a beautiful square wave anymore because we're on the other side of the resistor. You see that? So this is the square wave node here. But if there's any current flowing into this gate, which there is, we're charging up capacitors, this in is going to be, you get a voltage drop across our gen. And that's the origin of this here. So it goes up, it's very nice, and then right here is when transistors start turning on and off again. And it turns on and off. We have some Miller effect, which we get to talk about in 341. And this is suspiciously RC-like because it is. And then we go down inside the MOSFET here. There's lots of extra stuff. Remember the BS170, the N-channel MOSFET, had a whole lot of extra circuitry in there. Basically, it's modeling charge storage in the structure, so we can't suck charge out or take charge off of the gate infinitely fast or directly. There's some time constants involved. There's some resistances in series, lots of capacitances. That's what's going on. This goes up, we get this capacitive feed through this little bump here, and then it goes down, and so on, and it repeats again. So if we look at our, where are we at? Our error log, here's our numbers that we are looking for. Don't these waveforms look weird? I'll show you. Here's a preview. This is what you're going to see for the lab. So this is what I measured, let's see, last night. Built this circuit and got these two waveforms. So here is the input goes from low to high. The output goes from high to low. And we get it goes up, turns on around 1, 2, 3 volts or so. We get this flat part, it goes down. I was very careful in constructing with this. You will have to be very careful as well constructing it. Otherwise we'll get lots of ringing. Ring like a bell because of all the LC circuits we're making as part of constructing it. So when we construct this though, there's an extra capacitor, as you see, that is strapped across the power supply. Really, from a schematic point of view, it makes no sense. But what happens is these chargers are trying to flow really fast. The currents are changing really fast. Our wires from the power supply are really long, as in they're kind of big inductors. Well, if we put a capacitor there right across where we need the charge to come from, right at the power supply, points nodes on the breadboard, then we can do that. It makes this look a little better. And also we have to tie our ground leads as close as possible to the zero reference node on our circuit. So it's really, really tight. I used 3 pins on the breadboard, shoved them together, no wires, no extra wires, no jumpers or anything, just clipped right to the leads. It looks like a mess. It looks like a mess on the breadboard, but it looks beautiful on the oscilloscope screenshot. If we go to the other one, we see that the input goes down, goes all the way down, almost, turns off, MOSFETs turn off and on, and it comes up like this. This is okay. Let's look at one more weird thing. Let's not simulate the DC part, or let's simulate the transient simulation. That's what we did before. Let's do the DC sweep. So DC pulse, that DC, we can't do As you see, we can't do two simulations at the same time. That's annoying. Alright, so V pulse from 0 to VDD, it's parameterized, 1 millivolt. Okay. 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 That's weird. I'm going to delete this old one. DC sweep. There we go. Let's run the DC sweep. Now we know what it should look like. That's the easy one, right? Watch this. What's up with this? It says 0, 2.5. Why didn't our scale happen? So simulate. Plot the input. Plot the. Why did we only go up to 2.5? Let's explicitly say 5. Run again. Alright, so we're simulating, and H drive is still going. So we're stepping, step size, escape to quit. So we're going to try to stop simulating this. Alright, this is annoying. Do you see what's going on while my machine tries to deal with this? And stop simulation. Okay. Can we do it again? Can we do it again? No. Alright. So we're going to let this go for a while. See, here's inverter. Whoa. It's not supposed to go up. It's supposed to go and down, and that's it. Maybe some little jiggy-jaggy things, but that's it. No way. What's going on is, let's check this out. We'll go back to the models. The NMOS transistor, the BS170, has a threshold voltage of 2.9 volts. 2.9 volts, and here we go. We have the threshold voltage for the PMOS is minus 3.1. So if you think about that for a second, there's a time in this input that the input goes up. The PMOS transistor is on at this point, on. This is where the PMOS transistor turns off, but we have not yet turned on. We have to go all the way up to 2.9 volts to turn on the NMOS transistor. Between 1.8 volts and 3 volts, both transistors are off. And if you remember, when these transistors are off, when you measured them, they're very much off. SPICE is having a hard time. It's we have an off transistor, It's nearly an open circuit here. What's really happening is sub-threshold conduction. The gains of these transistors is really big, but these SPICE models were not the models that include sub-threshold conduction. What I'm going to do is we're going to add a sham resistor right here. And zoom in. Add this. Kind of a large value resistor. Let's call it 1 mega ohm. If we say 1 M, capital M, that doesn't work. That's milli. It's SPICE. If you want mega, you have to type MEG. Let's try to run it again. Hey, look at this. Oh my goodness, this is just weird. What we're ended up with is weird things happening because we're operating this in a weird way. How about 10K? Can we do that? Oh, that's nice. So what we did is we just gave SPICE a path for current to flow right here, and then it's still trying to figure this out. You see that? All right. That's all we have. Expect to see these sort of waveforms. If your setup is nice, measure these rise and fall times. They're going to be pretty close to what we measure.